this video, we're going to talk about using the models that we're building to make predictions and the notion of overfitting and what we can do to overcome that. So what do we mean by a prediction? Remember that our goal is to build a spam filter. We have data from a set of emails, and we know if each email is spam or not in truth, and we also know other features about them. We're using logistic regression to predict the probability that an incoming email is spam. And we can think about using a model selection approach to pick the model with the best predictive performance and stick with that one. But building a model to predict the probability that an email is spam is really only half the battle. We also need a decision rule about which emails get flagged as spam. So once we know the probability that the model predicts an email as spam, what a probability should we use as a cutoff to identify an email as spam or not? A simple approach would be to choose a single threshold probability, and any email that exceeds that probability is automatically gets flagged as spam. So let's take a look at an example. Here we have a logistic regression model where we're predicting spam or not. And this time we're using all of the predictors available to us from the data set to fit the model. So let's take a look at the code first. We're starting by defining our model, logistic reg, and then we're setting our engine to GLM for generalized linear models. And then in our model fit, our outcome variable is spam, and remember that's a factor variable. And on the other side of the formula, I have just a period. What this period stands for here is basically everything else available. So all of the other variables in the email data frame, so that's also the name of the data frame, is another thing we feed to this function, other than spam, obviously. So R is going to be smart about not putting the outcome variable that you've already defined on one side of the formula on the other side as well. So it's using all possible variables in the way that they're given to us. And we also define our family as well for our linking function. And then we can tidy up our results. And what I'm going to do is also print out all the possible rows in this table. That's the model outcome. So there are 22 rows in our output. One of them is our intercept, and the remaining 21 are the slope estimates that we have. So we can take a look here real quick and see what if anything makes sense. Remember, positive values would mean that higher values of that particular variable are more likely to be associated with the email being spam. So one example here is the word inherit, for example, as perhaps the number of times the word inherit shows up in the email, the more likely it is to be spam. So we're not yet focusing on exactly how to interpret this particular estimate that's given to us, but we're at least making some statements about the sign of that estimate. Now, going back to the code, you'll see a couple things here. First of all, I have a warning here that says fitted probabilities numerically 0 or 1 occurred. So that basically means that for some of the emails, the probability was calculated to be exactly 0 or exactly 1. And there are two reasons why this might happen. One of them might just be that is possible. You know, if you think that in whatever model data set that you're working with, if that makes sense for your model, that a probability of 0 or 1 could occur, then you might just take that as a warning and move on. It might also mean that with this many variables in our model, there are certain, especially potentially categorical variables, where the emails are perhaps, if it's a particular level of a given categorical variable, the email is always spam or always not spam. So if you basically start bucketing the data into these various categories, you're ending up with 0 counts in some of your buckets. So that's something we're going to come back to. But another thing that we might want to keep in mind is the fact that even if this was the perfect model that we could build, we've built this model specifically for the data set that we have, right? And we've used all of the data set in order to build this model. But truthfully, I don't really care about these particular emails. We already know if they're spam or not. What we want to do is to build a model that actually will accurately predict the future emails that one might get. So the mechanics of prediction is actually really easy. Once you have your linear model, you can plug in values of predictors to the model equation, calculate the predicted value of the response variable. We've given examples of this in the case of linear regression, both simple and multiple predictors, and we've also given an example of that in the case of logistic regression as well, where the math had a couple more steps, but ultimately we could simply calculate that probability pretty easily. But getting things right is hard. There's no guarantee that the model estimates you have are correct, or that your model will perform as well with new data as it did with your sample data. And so what do we do for this? We want to here talk about this notion of overfitting and underfitting, and then I have this okay level in between. So here we can see that in dark gray, our data, right? It's clearly curved. I think if you just look at the data, just the points, we can see kind of a curved down trend there. If I was to fit a linear regression through it, which is that dark purple line, it's definitely underfitting it, right? That is not what we would expect to fit through that. But on the other extreme end, the orange line is very jagged. So there I'm trying to almost get all of my data points accurately predicted, which it's not really doing all of them, but it's getting pretty close to them. So that looks more like playing connect the dots than actually fitting a curve. And in the middle, the pink curve is basically capturing the trend that's visible to the eye, but not trying to push further into trying to accurately predict every single data point. And that might just be the type of model that we want to stick with, because while the dark purple one is underfitting things, the orange line is considered to be overfitting because it's really trying to model everything about the sample data, and potentially at this point not just modeling the relationship in our between our explanatory and response variable, but any sort of random chance as well, which means that that model may not perform as well with the next data that might come in that may have arisen from the same random process. So we want to think about how do we spend our data in order not to find ourselves in a situation where the models that we fit are overfits. When we're doing modeling, we take several steps to create a useful model. We might do parameter estimation, we might do model selection, we might do performance assessment. And doing all of this on the entire data we have available can lead to what we call overfitting. Instead, what we want to do is to allocate specific subsets of data for different tasks, as opposed to allocating the largest possible amount to the model parameter estimation only, which is exactly what we've done so far. So in last week's videos and the earlier video for this week, we've used the entire data set that's available to us to fit a model so that we could start to wrap our heads around what a model is and what do we do with the model output once we have it. How do we use it to interpret the relationships in our data, and how do we use it to make predictions? But now we really want to be a little bit more smart about these things and think about, well, if I want to make sure that my model is doing a good job predicting things, I probably want to I probably want to avoid any overfitting. So how do we do that? We do this, a common way of addressing this is by splitting our data. So we split our data into two sets, training set and testing set. You can think about your training set as your sandbox for model building, just like you're on the playground. You can do whatever you want in there. You want to spend most of your time using the training set to develop your model. And this is usually majority of your data. A common split that's used is an 80-20 split, for example. So you take your data set and you take a random sample, perhaps, of 80% of it, and that's the data that you use. And the remaining 20% you don't get to touch until you're ready to test. So this is held in reserve to determine the efficacy of one or two chosen models. And you don't want to have that many candidate models that you're testing against it either, because it's really critical to only look at it once. Otherwise, it basically becomes part of the modeling process. And that's the remainder of your data, usually about 20%. So in general, in statistics, we talk about larger data sets are better, right? The more data we have, the more information we have. And this might feel like it goes kind of orthogonal to that, in the sense that We told you you have all this data, and now we're telling you you can't use all of it. It's not that you can't use all of it. In fact, obviously you do want to use all of it, but you're trying to use it smartly. You are trying to use majority of your data to build your model, but then you want to make sure that your model is not overfitting any sort of random patterns that might be apparent in your training data. And then to use the remainder of it to evaluate the models that you built. If we were living in a perfect world where there was infinite amount of data available to us for any sort of process that we're trying to model, maybe we wouldn't do this. We would just say, I'll build a model today, I'll get some more data tomorrow, and then use that for testing. But that's not a realistic situation. That's why ultimately we are using all of our data, but we're using it for different purposes. So how do we perform this split in R? We want to start by setting a seed. And what setting a seed does is it fixes the random numbers to enable the analysis to be reproducible when random numbers are used. So in this case, we're going to randomly sample 80% of our data to be our training set and the remainder to be our testing set, right? And so we want to set the seed both for the integrity of the model building so that every time we come back to this analysis, we're not seeing different observations in our training data. That would be like peeking into our testing data, but also to reduce our own frustration because every time you knit your document, for example, you don't want to working with a new data set. It's going to be hard to keep track of your process. So we start by setting a seed, and then we use the function called initial split, which takes our data set as the first argument. So that's the email data set that we're working with from the open intro package, and then takes a proportion to split into training and testing. So that prop is basically the proportion that should go into the training data. And remember that that's generally the majority of the data. And that creates basically a split object. And then we can use two functions called training and testing that will basically keep these, split these data actually into data frames that are called train data and test data. We could call these other things, but this will make it easier to keep track of them. Now, what's happening here is really no fancier than taking a random sample and then creating two separate data frames based off of that. But instead of using our usual dplyr tools for doing this, we are going to use functions from Tidy Models, because once you build your data using, once you split your data using these functions, the rest of the modeling becomes a lot easier to follow through, since the functions in Tidy Models are designed to work with objects that are the result of the training and the testing functions. So if we were to take a peek at the split, our train data has about, 3,137 observations, and our test data has 784 observations. And we can see that they both have the same number of columns, which is what we would expect. We're really splitting it in the rows. We're keeping all of the columns for both our training and testing data. You can think about that as the last time you get to look at the testing data, right? So we want to set that aside, and then let's work through our modeling workflow. So what we're going to do is we're going to start by fitting a model to the training set. So here I'm again starting with the logistic reg function, setting my engine to be GLM, and I'm going to fit a model that's spam versus everything else in my data set. So all of the other 20 variables. The data set that I'm using is not the full email data set, but the train data set. And then I define my family to be binomial since I'm doing logistic regression. And then I get this message again that we talked about a little bit earlier. So let's take a closer look to see why we might be getting this message. So here we have a bunch of plots for our categorical predictors. Those are on the x-axis, and the fill colors are whether the email is spam or not. Two things that should catch our attention are the from variable and the sent email variable. And we can take a closer look at those by tabulating the results. So from is whether the message was listed as from anyone. It's usually set by default for regular outgoing email. And sent email is an indicator for whether the sender had been sent an email in the last 30 days. Okay, so basically it's about, do you get a spam email from someone you had emailed in the last 30 days? And so with the from variable, we can see that there are no observations that fall in spam 0 and from 0, meaning that it is not a spam email and there is no from address that's set. So we are basically missing any observations in that bucket. And similarly with the sent email variable, we're also seeing that there are no cases where the email is spam, so that would be a 1, and sent email is 1 as well, meaning a person you yourself had emailed in the last 30 days then ends up sending you a spam email. And we would anticipate that to not happen, right? So in this case, these two variables basically have no observations in one of the buckets, so one of their levels, and then falls into one of the spam levels, which basically means that there's not a great separation in your data for those variables. So what we're going to basically say is that we're not going to use those variables in our model, because if you know that information, it's almost like you know whether the email would be spam or not. And that's not to say then we might as well just use those use those variables on their own and forget about everything else. It basically means that we don't have enough observations that fall into the other bucket that we would need some information on in order to be able to build our model. We can also take a look at the numerical predictors. So here is one, which is Viagra, which is how many times the word Viagra comes up in the emails. And I don't think the word Viagra is showing up so much in spam emails nowadays, but early 2010, so I think this was from 2012, I think that was a lot bigger of a spam keyword then. And we can basically see that, so if we take a look at our training data, there are no emails in our training data that have the word Viagra in it. So remember, we split our data. So there must have been some emails that had this word in our original data set, but in our training data, we have none of them. So we can't really use this variable for doing anything meaningful either. This also probably means that whatever emails did have the word Viagra in it, probably were very few of them to begin with, because, you know, we sampled 80% of our data and we ended up with none of those. Okay, so then what we're going to do is, in order to address that warning that we were getting and we were concerned about because we didn't anticipate our predicted probabilities to be exactly 0 or 1, we identified these variables that we know that should not be part of our model, and so we're going to subtract those out. So remember, we said that we can use basically the dot or the period to say all of the other variables, and then we can say, and then take out a few. Now, this would be equivalent to just listing all the other predictors separated by pluses, but that seemed like more work. So we might as well say, we're going to use everything but from sent email and Viagra variables. We are still fitting our model on our training data. And we basically have now a model output. We have some coefficients that are estimated for each one of our predictors. We're not going to focus on their magnitudes just yet, and we're definitely not focusing on this other information that's printed out here just yet, but at least we know that our model is producing no warnings and all the coefficient estimates are predicted so far, or estimated so far. Then we can use this model that we have fit, and remember that we use the _fit in our naming generally to say this is a model that's been fit, to basically make predictions with our testing data. So now we get to touch the other 20% of our data and make some predictions. And by default, this function predict is basically going to give us, for every single one of the emails in our testing data, whether the predicted class is 0 or 1, so not spam or spam. And here we've by default just printed out the first six rows of this. Not a very interesting thing to look at on its own. So let's do a little bit more here. So what we have done here is we're again using the predict function, the model that we have built using the training data, which is email fit, applying it to our test data to make our predictions. But this time the prediction type we want is probability. So I actually want to see the probabilities, as opposed to letting R decide for me whether the predicted value is 0 or 1 for spam based on a threshold of 0.5. So by default, it looks at the probability and says if it's more than 0.5, the probability to be spam, then I'll categorize it as spam. But I don't want it to make that decision for me. I actually want to look at the raw probabilities. And then I also want to bind columns to this from my, again, test data. I want to get the spam column from there so that I can take a look at the truth. And I also brought in the time variable, not because there's anything super exciting about time here, but it is different for each of the emails. So I can just, it allows me to take a look and make sure that these are different emails. It's almost like serving as an ID column in my head here. That's why I brought it in. So now this data frame that I constructed, the predicted probabilities, so that's the .pred0 is basically the predicted probability that the email in the testing data set is 0 in terms of spam, so it's not spam, or this is the predicted probability that it is spam. The sum of these two values for each row should basically add up to 1. And if it doesn't exactly, that's going to be just a rounding error. If we had more digits, we would see that they would be adding up. And then we have the spam column from the truth. So that's from the data that we'd set aside to begin with, what the truth column was. And then we have our time variable as well, just to serve as an ID again. So the first 6 observations, let's take a look. The predicted probability that the email is not spam is 0.942, so pretty high. And the truth was that it was not spam, so doing good. Another one, predicted probability that the email is not spam is 0.92, so pretty high, and the email was in fact not spam. Or I can look at the other column. For the third row, the predicted probability that the email is spam is only 9.6%, and that's less than 0.5, so we can say that's small, and in fact, the truth is that the email was not spam. Now, this is looking like we have a 100% hit rate here, but that's only true for the first 6 observations. We can take a closer look. So what I've done here is I've sorted the data or arranged the data based on the probabilities of spam. So the predicted probability of spam in descending order. So this particular email, for example, the first one had a pretty high likelihood or probability of being spam, and in fact it was. And similarly, the second one, again, pretty high probability of being spam, and in fact it was. But let's take a look at this third one. 0.592, so greater than 0.5, probability that the email was spam, but actually it's not. So the model gives it a pretty decent probability that the email is spam, but turns out in truth it's not. So in that case, we have made a mistake. And here's another one of those. The predicted probability that the email is spam is 0.531, but in reality, it was not a spam email. So we don't have 100% hit rate here, and we didn't anticipate having so, right? We anticipated that we actually might have some false positives or false negatives here. So going through these one by one, if I scroll back to the previous slide, going through these one by one, we could even take a look at some of the other features of these particular emails to try to reason, oh, I wonder why. The email thought it would have been spam, but it actually wasn't. But that's not going to be, and going through that process can be informative for your model building perhaps, but what we really want is some sort of a measure that can give us a summary of what's going on kind of overall, right? So one of the things that we use for this is called a receiver operating characteristic, or an ROC curve. You will hear of these as referred to as ROC curve. The C does not stand for curve there. That's the characteristic, so it's not redundant. And you'll rarely hear anyone say receiver operating characteristic. They're always referred to as ROC curve. If you're curious why they're called that, it actually has to do with where they were developed. So they were originally developed for operators of military radar receivers. So that's where the name comes from. So there's no like hidden statistical meaning there. But what they show us is a plot of sensitivity versus 1 minus specificity. So to be, I think, a little bit more clear, we could call them true positive rate versus false positive rate. So remember, we would want our true positive rate to be as high as possible. And if possible, we would want our false positive rate to be 0. So ideally, we would want this curve to go all the way up, and basically thinking about those different thresholds for deciding whether an email is spam or not. Even if that went up on the y-axis, we would ideally not want the false positive rate to increase. So an ideal one would be a vertical line up and then over. That's rarely the case. Each of these little jagged edges, you can think about them as where a decision was made and a decision was made incorrectly. So to draw this curve, we can use, so we're looking at our, the prediction data frame, right? So that actually has our predictive probabilities in there. And then we're using the rock curve function, so rock underscore curve function, again from Tidy Models. We have to tell it which column is the truth. So that was the spam column. And then we have to tell it which probability to use to draw the curve. And then another thing that you might need to do is to tell it which level, so is it the first level or the second level of your outcome variable is the one you're calling success. In our case, the spread 1 is the second level. By default, it would use the first one. So we basically are looking at the probability of being classified as spam, not the other way around. So that's why I've also added this additional argument event level second. And ggplot actually can automatically make this ROC curve for you. So instead of going into the detail of how to draw that jagged line, we want to focus on interpreting that. And again, remember that ideally we would want that curve to shoot up all the way and then over, giving us an area under the curve of 1. You can think about that diagonal, the dashed diagonal that we get there, as basically the 0.5 or flipping a coin. What if we were just flipping coins for every single incoming email? That's where things would land then, as opposed to using your model to make a more informed decision. So if your ROC curve ever dips under that, then you know that you're doing worse than flipping a coin. As long as you're above it, you're doing better. But we can think about comparing ROC curves for different models to see which one is doing a better job at predicting. We can also numerically calculate the area underneath that curve. So for that, we would use the function ROC-AUC. So that's basically area under the curve. And you can see basically that the arguments that it takes is exactly the same as the earlier one. And the area under the curve is 0.828. That number on its own, the fact that it's greater than 0.5 is good, but that number on its own is not very meaningful. But it might be meaningful if you compare it to a different model you can build with these data and then see which one is doing better in terms of the area under the ROC curve.